YouTube live has been giving me some trouble lately. And this morning also it was giving me some trouble. So I'm setting it up. Just give me 1 second. Okay. All right. So is it updating? I don't know if it's updating. Okay. All right. So hello everybody. Good morning. I'll start the recording also. Okay. All right. So good morning everybody. Today I will be talking about coherent states. Okay. So what I'm going to do is I am going to continue so what this course will be from this point on, basically it will be a continuation of the BTech course, right? Now in the BTech course, I've covered all the basics of quantum mechanics, entanglement, Schrodinger's equation, single particle in a potential well, and also harmonic oscillator, then other things, entanglement, measurement, and bracket notation, and so on and so forth. So all of these topics, I think that I have already covered with you all, right? I mean, the basics. These are the basics, right? So if you feel that some of these topics are not yet proper, if you have doubts about them and you would like me to go over any of them, then you can let me know and I will do so, okay? But the thing is that so I will treat this as a continuation of the BTech course, all right? There are many BTech students also. There are some BTech students also who are continuing to attend these courses, classes. So I have talked about the harmonic oscillator, right, up till now. So is this okay with everybody? Does anybody have any issues or concern with what I just said? Okay. All right. Well, if you do, you please let me know. Okay.
Sir.
Now, so in the second. Okay. So in the up till the previous most recent class that we had, right? I talked about the harmonic oscillator, and so what we find is that the harmonic oscillator, there is a certain energy in the ground state, right? And that's h bar omega by 2. And then there is also a certain minimum uncertainty, right? Which comes from the fact that, well, you know, if you look at the diagram in the phase space and you try to like pin the trajectory of the particle down, you can't do that, right? You can only like define it up to some delta x and delta p, so within some fuzzy region of phase space. And because of that fuzzy region of phase space, right, that fuzzy region of phase space has a certain minimum area. And that area is a measure of the uncertainty in your system, in your theory. Now, this brings us to the next topic, which builds up from harmonic oscillators, which is the question of coherent states. Okay. Now, these states are very important. If you study quantum optics, for instance, these are very, very important. Then, if you want to study the quantum to classical transition, that is how does a quantum state become classical, and what limit can we treat a quantum state as a classical state? I'm trying to get the angle right so that the background is not okay. So this is these states are very important. Then there are many other applications, but so it's used in general for quantum mechanics. So many. Okay. Now, so what are coherent states, and why are they so nice? Coherent states are states of minimum uncertainty. Okay. So you know that we have this uncertainty principle, right? And just to remind you, this uncertainty principle comes from the fact that if you have any two operators, so where A and B are any two operators, and this is the commutator of A and B. And if A and B don't commute with each other, then the commutator is not zero. So when this is the case, what will happen is any attempt to measure A and B simultaneously will lead to some minimum uncertainty in both of these observables. And that minimum uncertainty is given by this relationship. And what this says is delta A times delta B is greater than or equal to this expression. Now, this I have explained in one of my previous lectures. So I think you all have covered that lecture. Can somebody tell me yes or no?
Yes, sir.
MSc people?
Yes, sir.
Anybody?
Yes, sir.
Sudeep, Adra?
Yes.
Yes, sir.
Yes, sir. Yes, sir. Yes.
Can you please give me a response?
Yes, sir.
Yes, sir.
Have you seen this before in the lectures I asked you to watch or not?
Yes, sir.
Huh?
Yes, sir.
I can't hear anybody. Are you guys saying something? Oh, okay. All right. So Yash is saying yes. Okay. So I won't go over this again. All right. And if you want to go over it, you should watch that lecture. And also, this is covered in some of the homework problems. So this is the uncertainty. This is the Heisenberg principle, right? And it applies to any two operators which don't commute. Now, the thing is that for classical states, right, we have well-defined trajectories in phase space, right? So for example, if I look at the harmonic oscillator, okay, and this is the harmonic oscillator with 1 degree of freedom in one dimension, and I draw the trajectory of what its motion looks like in the phase space. It looks like this, right? And the thing is that you can write down the exact solution of the equations of motion for each point on this line, right? You have x of t can be written as and then p of t is mx dot t, right? It's the momentum, and so this just becomes m times, so you will get a factor of omega when you take the derivative of these with respect to t. You will get m omega minus a sine omega t plus b cosine omega t. Right? So we have a well-defined equation for both x and for t, right? And we can plot this trajectory for any given value of omega. Now the thing is that what happens in the quantum case? Well, for the quantum harmonic oscillator, your system is now described by a state, right? And we have seen one example of one basis of these states. So one basis of the Hilbert space is given by these number operator eigenstates. Right? And so any state of the system, an arbitrary state, right? We can write the state as a superposition of these basis states. Yes? Because this is an orthogonal basis, right? So it's an orthonormal basis, and this is delta of Mn. Now, so then the question becomes, if I have a state of this form, right? What is its, right? There are several questions. How to describe, for instance, the time evolution of the state, right? Okay. Then what happens to the position operators and the momentum operators? And what is the corresponding picture in phase space? So, and again, we should be very careful to note that this is the, when we talk about this phase space, this describes the classical system. So what is the picture in classical phase space in terms of X and P, right? So we don't have an answer to these questions. We would like an answer there. So now, before doing all this, right? So we should first ask ourselves, so what happens to X and P, right? Well, X becomes an operator, X hat, and P becomes an operator, P hat, right? And there is a relationship between these operators and this A dagger and A operators, right? I should put hats on these A's also, just to distinguish them. And what is that relationship? Well, let's go back to the definition of A dagger and A. And where is that definition? So this is the definition of these operators in terms of X and P, right? And again, I can write. It helps if I work with dimensionless variables, right? So if I redefine my X and P, okay, so if I redefine my X and P to be my operator X prime is this m omega by 2 h bar X hat, and my operator P prime is 1 over 2 m h bar omega P hat. Then I can just write A and A dagger are linear combinations of this X prime and I prime. I can do everything in terms of these prime variables. At some point when I want to convert back to the unprimed ones, I can just insert this expression, okay? So I have this A is equal to X plus IP. So let me write that again. A is equal to X prime plus I P prime, and A dagger is equal to X prime minus I P prime, right? Now, we can easily see from this expression that we can invert this, and we can invert this if we just add both of these expressions together and divide by 1/2. I'll get A plus A dagger is X prime hat, right? And P prime hat will become A dagger minus A minus A dagger divided by 2i, right? I mean, you can just look at this expression, the first line, and you can just add and subtract, and you get this expression. Fine. So once I have these expressions, right, now I can do something of this kind. For example, I can ask, what is the expectation value of the position or the expectation value of the momentum in any of these given states, right? So as I told you earlier, any state, right, can be written as a sum of these number operator eigenstates, right? So if I want to calculate any of these expectation values, if I want to calculate the expectation value for any operator, what will it be? It will basically boil down to so what I'm doing here is I'm substituting the expansion for the state psi in terms of this in basis states. And what will this become? This will become summation of n comma n prime 1 to infinity Cn prime Cn and then n prime operator n, right? So if I want to calculate the expectation value of any operator in any state, right? It doesn't matter what the state is. I have to find out this object, right? And what is this object? So whenever we have any operator, and we have some set of basis states Aij, then this is also written as Oij, right? So this is now a matrix, and these are known as the matrix elements of O, okay? But very important, depends on the choice of basis, right? This is very important. You have to keep that in mind. So if you choose a different basis for your Hilbert space, then your matrix elements will change. Okay. So what we have, what does this become? This becomes sum over n prime C n prime or C multiplied by O n prime n. Or let me write that again here for clarity. So kind of squeeze everything here. Okay. So what I have to do is I have to determine the matrix elements of this operator n prime and n, right? So as an example, let's say that let's ask, well, what happens if we try to determine the matrix elements of what is the matrix element of the operator A? Okay. So the matrix elements of the operator A would be written as n prime A n, right? And so I can write this as A n prime n. And now, what is A dagger acting on n? Anybody? What is this? Do you remember? You really should remember this. Okay. So this is very, very important. Something you use all the time. So this is A acting on N, right? So then we can substitute this expression over here. And what do we find? We find N prime root N minus 1. Now root of N is just a number, right? So I can write it like this, N prime N minus 1. Okay. So, and what is this expression? Anybody? What is the inner product of N prime and N minus 1?
0.
Varun?
0.
Shubham?
Delta n prime n minus 1.
Anybody? Sudeep?
Delta
Are you guys
n.
saying something? Can somebody say something? Because I don't know if you're saying something and I can't hear you.
Hello, sir. Hello. Hello, sir.
Can somebody say hello?
Hello, sir.
Ah, you can't hear me. Okay, 1 second. Huh? Just give me 1 second. Let me this thing. Okay. Okay. Try now.
Hello, sir.
Somebody say something.
Hello, sir. Hello, sir.
Okay. Let me.
Hello, sir.
All right. Can you hear me now?
Yes, sir.
Nishita, can you hear me? Okay, good. And I can hear some noises from your end. Okay. So what is this? Oops. Sorry. What? So I don't know if anybody asked any questions. I missed that because for some reason my incoming audio was not working. So if you have any questions, you can please ask them now. And also, what is this expression? Somebody was telling me.
Are
Del
there
n.
orthogonal space?
Huh?
They are orthogonal space, right?
Yeah,
So
they're
zero.
all right. It's an orthonormal basis, right? So this will be what? Come on. Anybody?
N prime n minus 1.
N prime n minus 1 what? How will I write it mathematically?
Delta n prime
Delta
n minus
delta.
Right? This is delta n prime n minus 1. And what is this? This is the matrix element of A. So I can write it as A prime or A n prime n. Okay. The same way I can calculate the matrix element of A dagger. So I have n prime A dagger n. A dagger acting on n gives me root of n plus 1, right? So this tells me A dagger n prime n is equal to root of n plus 1 delta n prime comma n plus 1. And just for okay, so you can see that there is a sort of a nice pattern here. And Now, once we have this, we can ask, for example, what is the expectation value of the momentum? What is x hat? What is p hat, etc. Right? Why? Because we know that x prime and p prime can be written in terms of sums of a dagger and a, right? So let's ask what is this x. First, let's ask what is this x n prime prime. What is the matrix element of x, the operator x? Okay. So this is just 1/2 n prime a plus a dagger n, right? So what is this? This just becomes 1/2 times the matrix element of A plus the matrix element of A dagger, right? And I can just copy the answer from here. So this tells me that x n n prime is 1/2, and this was root n delta n prime n minus 1 plus root of n plus 1 delta n prime n plus 1, right? Now, just a couple of remarks about the form of these matrices. So you have this matrix, for instance. What does this look like? If I right, what do these matrices look like? We can learn a lot just by looking at the matrices. So, for example, this looks like some root of n delta n prime n minus 1. Now, first of all, in terms of a matrix, this is a matrix in which all the elements, whichever are non-zero, so all non-zero elements, okay, no, wait, 1 second. So let's look at a matrix representation. Okay. Now, for a harmonic oscillator, remember n is infinite, right? N goes from 1 to infinity. So technically, if you ask how many rows and columns are there in this matrix, there are an infinite number of rows and columns, right? So this is a n prime n. So the first index is the row, the second index is the column, right? But we don't need to worry about the fact that it is infinite dimensional. We just need to look at the general pattern. Now, the first thing we can see is that the diagonal elements are 0, right? The diagonal elements are all 0. Okay. Now, for n prime is equal to, what is n prime? N prime is the row. So let's look at the first row. For n prime is equal to 1, what is the value of n minus 1? So if n prime is equal to 1, right, then n minus 1 has to be equal to 1. That gives you the non-zero number, right? So that means n has to be equal to 2. Okay. So what you will find is that the non-zero component, one of the non-zero components, comes from A12. And what is the value of A12? It's root 2 root n, right? Delta 1 and 1, right? So it's just root 2, right? So this is n prime and this is n prime minus 1, basically, right? 1 less. So you can see that all the non-zero entries will be of this form, right? Of the form n prime is equal to n minus 1, right? So in other words, all the non-zero entries will be over here in the upper diagonal. And what will be the values, for instance? This will be root 3, so on, root n. I'll just put capital N instead of infinity. I'll just put capital N, okay? It's understood that capital N goes to infinity. So all of these are non-zero, and the values go like root 3, root 2, root 3, and so on till root n, and actually goes on till infinity, right? And everything else is 0, and everything else is 0. Right? So you can see that this is a off diagonal matrix, right? All of these elements are off diagonal. So there are names for all sorts of matrices. Okay. Shubham, this is not an antisymmetric matrix. This is not a symmetric matrix. This is not an antisymmetric matrix. See, these operators A and A dagger, they are not Hermitian operators, right? Okay. So the same way, if we write down the matrix elements of the A dagger operator, this is root n minus 1 delta n prime comma n minus 1, sorry, n plus 1. So now you will have, what will happen? Only the elements which are below the diagonal will be non-zero, right? You can see that, I hope, right? So all the elements above the diagonal will be 0, and all the elements below the diagonal will, so only the elements here in the first off diagonal column or the off diagonal will be non-zero. And what will be the values? The first one, for example, will be A dagger 2, 1, right? And that will just be equal to, so this will be the root of n plus 1. Just to be careful, root n, and this is root n plus 1. Right? Yeah, root of n plus 1. Right. So this will be root 2. So you will get here, you will get root 2, then root 3, right? So on, let's say till root n. Okay. So let me put that a little bit over here. All right. So this is again an off diagonal matrix. Now, so from this expression, right, from the form of these expressions, we can easily see what the form of the this position operator, what will be the matrix elements of the position operator? Well, it's just the sum of these two matrices, right? So the sum of these two matrices will be what? You will get these terms in the upper off diagonal, and you will get these terms in the lower off diagonal, right? And divided by 1/2. So you can just write x hat is equal to or x n prime n is equal to, right, 1/2. The green numbers denote the row and column numbers, right? √2, √3, and so on till 10. And now you can see clearly, for example, that this is a symmetric matrix, right? This is a symmetric, and also it's also a real matrix, right? So this implies that the operator X is Hermitian. Okay. What about the operator P? The operator P one can do in a similar manner, right? I'll leave that for you as your homework number 5, question 1. Write down matrix elements for momentum operator. Okay. So Shubham, I'm not taking the diagonal element to be zero. The diagonal element is 0, right? Because this is not a diagonal matrix, right? If you have a matrix of the form delta ij, then what is this? This is a diagonal matrix, right? But if I have delta ij plus minus 1, then this will be off diagonal, right? Because here I has to be equal to j, and here I has to be equal to j plus or minus 1. Okay. Okay, so now that we have this kind of a picture, we can now ask what happens for the expectation value of the operator in a general state, right? In an arbitrary state. So in particular, for instance, one can ask what is the expectation value of the this thing X operator, let's say in this state, right? And what is this? Anybody?
0.
It's 0. Yeah. You can see that, right? The expectation value of X is also the off diagonal elements. Oh, sorry, the diagonal elements, and they're all 0 in this. So the expectation value of both the momentum operator and the position operator in any of these eigenstates, in any single eigenstate, is 0, right? So if you want a non-zero expectation value, let's say, of the position and momentum operator, you will need to have a superposition of states. So let me write an example of such a state. Let me say psi is equal to 1 by √2 root n, something like this, root n minus 1 plus root n plus root n plus 1. And this will have to be equal to 3, 1 by √3. right? Okay, so now I can ask, what is the expectation value of the position operator in this state, right? So now you can just work that out. Well, this state is what? N minus 1, n plus 1, right? This is one copy of the state, and let's put this here, and then in the middle you will put x, and then again you have the state n minus 1 plus n plus n. Okay, and notice that here there is no sum over n, right? So I am choosing a fixed value of n, whatever it is, let's say 10 or 20 or whatever. So then this is a superposition of the 9 plus 10 plus 11, right? That's why here I'm not writing n prime. Okay, I'm using the same n because it is the same n. N is a fixed number here. So if you look at this, well, this becomes 1 by 9, right? And you will have 9 matrix elements. You'll get 9 times x prime n minus 1 n minus 1, right? X prime n comma n minus 1, and so on. And now you know that for x, which are the non-zero components? They are n comma n plus 1 and n comma n minus 1, right? So everything which looks like this, the diagonal components, they will all go to 0, right? And then there will be, so let me write down the full thing, okay? N plus 1 comma n plus 1. So we have 9 terms. And yeah, sorry, I should not put the hat here because these are the matrix elements. Hat n comma n plus 1. Okay. And now in this, all the diagonal elements are 0. Which other elements are 0? This one. This is 0. This is 0. Right? Whichever terms are not related to each other in this way. So I get, and this one I should rewrite n minus 1 comma n. So this becomes, the non-zero elements become x n minus 1, x n minus 1 comma n plus 1 comma n plus x n comma n plus 1. Right? So n is an integer, right? N is an integer, Shubham. N is an integer. We have worked this out in the previous lecture on the harmonic oscillator, right? And now these numbers, we know what they are. These numbers, we know what they are. We can just put them in here. So again, I'll put homework number 5, question 2. One question I've already given you. Write down the matrix elements for the momentum operator. this I will give you, right? So evaluate the expectation value of the momentum and the position operators for the state psi is equal to okay, but this I worked out for you basically, right? I mean the X part I've already worked out for you. So we'll make it a little bit more interesting. Evaluate the expectation value of the momentum squared and the position squared in this state. Okay. And for this, I'll give you a little bit of a hint, since at some point you might get lost. Ah, yes. Thank you for pointing that out, Vipul. This is √3 and √3. So this should be 1/3 and 1. Okay. So what will happen when you, for example, when you take x square, right? So x square will be 1/4 a plus a dagger square. So you'll get terms like this. You'll get a square, you'll get a dagger square, right? You'll get a dagger and a dagger a like this. Okay. So then how do you evaluate something like this? So let's say you have to evaluate this and then a dagger a n. Okay. Now again, the procedure is very simple. A acting on n will give me √n minus 1, right? So I'll get √n times n prime times a dagger n minus 1. And now a dagger acting on n minus 1 will also give me √n. So I'll get n times n prime n, which will become n times delta n. Of course, you can see that this is just a number operator. So the number operator acting on this will just give you n. So there is no big surprise here. But for the other terms, you will get non-trivial expressions. You will get things like delta n prime n plus minus 2 and so on. Okay. So this is your hint. All right. So I'll leave it here. Let's see, any questions on the YouTube live chat? No questions. Okay. Any questions from you all? See, if you're confused about some of the things, my suggestion would be to go back and look at the previous lectures on the harmonic oscillator. Okay. Also, as far as references are concerned, I'll send you a reference. Okay. The thing is, I don't have any one reference. I just use sources from all over. Right. Mostly my reference is just Google. Okay. All right. So if there are no questions on the live recording, I'll